Well, there's a lot of applications to these transcendental functions. These exponential functions is what we're going to focus on, as well as a little bit of logistic growth at the end of this section. And here's our exponential growth and decay model that we're going to use. A of t is the amount, the population amount that we have after time t. A sub 0 is the original amount of the population at time 0. E, of course, is the irrational E, and K is our growth or decay constant. So we need to find a growth or decay constant that's unique to this scenario. So let's go ahead and look at this first one. So this one says, at the start of the experiment, we have 125 cells. So that's A sub 0. That's the current original population. 3 hours later, there's 235. So A of 3 hours later ends up being 235. So let's go ahead and write this scenario and let's solve for the growth rate, K. Okay. So first of all, we have 125 of these. And then it says after 3 hours, we end up with 235. So I'm going to replace the A of t, or A of 3, with 235. There's 235 cells after 3 hours. So t is 3. Now we're going to go ahead and divide both sides by 125. So I have 235 divided by 125, which is 1.88. So e to the 3k equals 1.88. Now I got to undo e, so I'm going to run the natural log on both sides. So 3k equals the ln of 1.88. Now I divide by 3 on both sides. So ln of 1.88 divided by 3, and that's our k. So I'm going to go ln of 1.88 and then divide it by 3. 0.210423926. Okay. So now we have our model. We started out with 125 cells, that's A0, and now we have our K, 0.210423926 T. There's our formula. And so we can figure out how many cells from that formula, how many cells we have after 5 hours. And you can, if you want to round that K, I probably wouldn't do anything much less than 6. You could probably get away with 4 decimals on that. But the idea is that you keep that out to as many digits as you can. So you can keep that in your memory on your calculator would be a great thing to do. Okay. And now we're just going to punch this in for 5. That's what I meant to do here, 5. And let's punch that in. Let's see what we get. Go ahead and punch that into decimals there, you guys. Get 357.964. No. Rounded to the nearest cell, so 358 cells approximately after 5 hours. Okay. Now this last part says, well, how long, so in other words, what's the time t, how long does it take for the population to reach 442 cells? So 442 is going to go in for my A of t. So 442 divide by, so 442, divide by 125, 3.536, e to that. Now I'm going to take the natural log of both sides. And so we've got the ln of 3.536 equals 0.210423926t. I'm going to divide both sides by that. 0.2104 blah 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 blah. And so t is 6.00215 blah blah blah. So approximately 6 hours if I round to the nearest hour on that. Next scenario, now this time we have at the start is 1,000 bacteria. That's our A sub 0. After 4 hours, the population doubled. So now, this is saying A of t ends up being double the initial amount. Well, double the initial amount. Well, I started with 1,000. After 4 hours, I say I must have 2,000 then. I must have double. Does that make sense? So let's go ahead and do the growth formula. A of t equals A sub 0 e to the kt. We started with 1,000. After 4 hours, I have double. I have 2,000. So I'm going to divide both sides by 1,000. So we have 2 equals e to the 4k. Now I got to take the natural log of both sides to undo the e. So I have ln of 2 equals 4k. And I divide both sides by 4. So k ends up being the ln of 2 divided by 4. K ends up being the ln of 2 divided by 4. Well, if I punch in the ln of 2 and divide it by 4, I get 0.173286795, blah, blah, blah. Right? We'll just do it to there. So the formula is A sub 0, I started with 1,000, e to that k value we just found, t. And so then we can do part B. Well, how many bacteria are present after 6 hours then? If we plug t in for 6 in for t. Plug a 6 in for t. So I'm going to go that number times 6. So 6 times 0.173 blah 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 is 1.039720771. Now I'm going to go e to that. And I get 2.828427125 blah 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 times it by 1,000. And we get 2828.427125, or round to the nearest bacteria cell, 2828. Okay, so we did, and that's again with no rounding error there, right? I didn't cut anything off for my K. You know, if I cut that off a little earlier, I'm going to have some rounding error on that. All right, this next one's got a population. It's given it to us in a table. And notice it shows in the year 2000, this is like year 0. In the year 2000, there's 53.4 million people in whatever city this is. Tell us how many there are in 2011. Well, 2011 is how many years later? 11, exactly. And then it gives us the population growth rate. So here's our K, 0.0108. So let's go ahead and set this up. So in year 0, there's 53.4 million, and this city grows at a rate of 1.0108 for the K. Okay, growth rate there. Now we just find it for year 11, 2011, 11 years later. And we just got to punch that in. Let's see what that gives us. $53.4 times e to the, what was that, 0.0108 times 11. So 60.136125. So in the year 2011, let's say we round it to the nearest tenth, 60.1 million people in 2011. That's what that's saying, right? All right, now let's focus on decay, half-life problems. So these are exponential decay. So half-life is when they give you a half-life. So this first one they say the half-life of strontium-90 is 28 years. So what they're saying is in 28 years, if T is 28, I have half my original amount is what I end up with. Whatever A sub 0 the original amount is, after 28 years, I have half of it. That's the half-life for strontium-98. Okay, so what I'm going to do is we're going to divide both sides by A sub 0. So I have a half equals e to the 28k. So e to the 28k equals a half. I take the natural log on both sides to undo e. So I have 28k equals, and remember ln of 1 over 2 is the ln of 1 minus the ln of 2. And the natural log of 1 is 0. So 28k is negative ln of 2 divided by 28. So I have negative ln of 2 over 28. That's where this comes from. But I'm going to go ahead and solve it each time because I like to go through that practice to find my k. So my k is, and let me punch that in, negative ln of 2 divided by 28 is, so my k is negative 0.0247555256. So now they ask us, what's the decay function if the initial amount was, the initial sample was 10 grams, so A sub 0 is 10 grams, and now we have our K, negative 0.0247555256 T. And now we can use that to figure out how much of a 10-gram sample is left after 11 years. After 11 years, using this, how much would I have left? Now, if I started with 10, remember the half-life is 28 years. If I started with 10 grams, after 28 years, I would have 5 grams. I'd have half that amount, right? That's what this is based on. That's what our K is based on. Well, we're not going for 28 years. We're only going for 11 years. So I should have more than 5, right? Somewhere between 10 and 5 is how many grams we should have left. So I'm going to take that negative 0.0247 blah, blah, blah times 11. And I get 10 e to the negative 0.2723 blah, blah, blah. Now I'm going to go e to that answer. And that's 0.7616. I'm going to multiply that by 10 in front. So approximately 7.6 grams or 7.62 or whatever, right? With no rounding error there. You could try this one. It'd be a good time to pause it and try this similar type of a problem. You get a half-life of this radium-226 is 1620 years, right? So it takes It takes 1,620 years to have half the original amount. Divide by a sub 0. Take the natural log of both sides. So the ln of a half equals 1620k. Remember, that's ln of 1 minus the ln of 2. ln of 1 is 0. So you have 1620k is negative ln of 2 because the natural log of 1 is 0 divided by 1620. And that's our k. Negative ln of 2 over 1620. Negative ln of 2 divided by 1620. So negative 0.000427869, blah, blah, blah. That's our k. So now we can write it. Part 2, how much of the 2 gram sample? So you're starting out with 2 grams. A sub 0 is 2. Now we know our k. And by the way, you could leave that. You could use k as this in the formula instead. That's fine. In fact, even better, right? But we're trying to figure out how much we have left after 1,000 years. So I'm going to go 1,000 times that k, which is negative 0.42786. And then I'm going to go e to that, 0.65189, and then times 2 in front. So I have 1.303794098. So after 1,000 years, there's approximately 1.3 grams left. Remember, it takes the 1,620 years to have half the amount, right? We started with 2 grams. After 1,620 years, I'd have 1 gram, right? So after 1,000, I'm not going to be down to 1, right? I'll be at 1.3, it looks like. All right, let's get into our Newton's law of cooling. So with Newton's law of cooling, this is the scenario where you take something out of the oven that has an initial temperature and you let it sit in your room temperature, and eventually it's going to be whatever the room temperature is, right? But this will tell you how fast it gets to whatever degrees. So here's the formula. Let's do the scenario here. Capital T is the temperature of the surrounding medium. U sub 0 is the initial temperature right out of the oven, or whatever the initial temperature is, where it's at. K is how fast it cools off. T is our time. So this one says a pizza is removed from the oven and it has a temperature of 450 degrees. That's the 450 right there. That's our U sub 0. Now it's left in a room that has a temperature of 70 degrees. So that's the temperature of the surrounding medium, is the capital T. Now we're going to have to solve for K here, but they gives us some more information. After 5 minutes, that's our time T is in here, is in minutes here. The temperature of the pizza, so U of 5 is 300. That's U after 5 minutes is 300. Now we can solve for K, and we'll know how fast the pizza is cooling off. Because we got to find that K constant, the cooling constant, which will be negative here. So we got 300 equals 70 plus, what's that, 380? E to the 5K. Subtract 70 from both sides. So 230 equals 380 e to the 5k divided by 380. So I have 230 divided by 380, 0.605, 263,158 equals e to the 5k. Again, I divided both sides by 380. Now I got to take the natural log of both sides. And so we have ln of e to the 5k is just 5k equals the ln 0.605, 263,158, blah, 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 divided by 5. So that's our k. So ln that, then divide by 5. Negative 0.100418389. That's our k. So now we have this scenario. We have the temperature after time t is 70, T, capital T. The initial temperature was 450 minus 70, e to that k, negative 0.1004, blah, 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 times t. There's our model. So it says, what's the temperature after 20 minutes? So just plug in 20. What's the temperature after 20 minutes? Well, plug it in. This will end up being approximately 121 degrees Fahrenheit. Okay? Punch that all in. Now, the second part, when will the temperature, so solve for u of t. I'm sorry, when, so how long, t, solve for t. When will the temperature of the pizza be? 140. So 140 is my u of t. 70 plus that 380 e to the negative 0.1004, blah, 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 t. Let's solve for t. So let's solve for t. Divide by 380 both sides. 0.1842, blah, 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 equals e to the negative 0.1004 t. Take the ln of both sides. So I have negative 0.1004 t equals the ln of 0.1842, blah, 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 divide by negative 0.1004, blah, 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 and t ends up being approximately 17 minutes. So it takes 17 minutes for the pizza to get down to 140 degrees when it's coming out of an oven of 450 degrees, sitting in a room of 70 degrees. That's what that's saying. All right, this is a good U-try problem if you want to, but we'll go ahead and map this out. So a thermometer of reading 72 degrees placed in a refrigerator where the temperature is a constant 38 degrees. So this is the temperature of the surrounding medium. We're going to put the thermometer into the refrigerator. So eventually it'll be 38 degrees, right? But the thermometer initially reads is 72 degrees going in. Now it says after 2 minutes, the temperature is 60 degrees. So e to the 2k equals 22 over 34.6471. Take the natural log, both sides. So 2k equals ln 0.6471 divided by 2. And so our k approximately negative 0.2177. So now we've got the equation here. The surrounding medium, the refrigerator is 38 degrees. I started, the reading was, the thermometer was 72 degrees initially. And now we've got the K, negative 0.2177 T. And now what we'll do is what will it read after 7 minutes? Let's plug 7 in. This ends up being 45.41 degrees Fahrenheit. You punch that in. Second question, how long will it read before it takes 39 degrees? Will it be 39? So U of T is 39. Solve for T. How many minutes will it take to do that? Well, let's subtract 38 from both sides. Divide by 34, so divide both sides by, so 1 over 34. Now I take the natural log. And I can divide by negative 0.2177. And T ends up being 16.2 minutes. So it takes 16.2 minutes for it to get to 39 degrees. All right, the last model is a logistic growth model. So if you have a petri dish, bacteria inside, the bacteria grow exponentially, but not forever. Once all the food is used up, the growth will level off. Can you kind of see how it's leveling off here? It's approaching a horizontal asymptote. So logistic growth model best describes this. A, B, C are constants, and the C value is what the growth will level off at. In other words, it's the horizontal asymptote, it's the limiting factor. Okay, and the terms A and B will go to 0 as T approaches infinity, and B is our growth rate. Okay, so let's look at this first scenario. The population in Canada since January 1st, 1900 can be approximated with this logistic growth model. Evaluate P of 0, and what's its meaning? Well, that's T is the number of years since 1900, so if T is 0, that's the population in the year 1900. So let's plug it in. Well, e to the 0, right? This is 0 up here. 0 times negative 0.20505 is 0. E to the 0 is 1. So I have 1 plus 9.6 times 1. So P of 0 is 55.1 over 10.6. So I punch that in, and I end up with 5.2. And this is in millions. So in the year, in other words, in the year 1900, there was 5.2 million people in Canada. So what's the growth rate? Well, that's the B value. That's the B value, so it's this right there, negative point, whoops, let me do it in yellow here, negative 0.025. That's the growth rate. In other words, it's 2.515%.
Would be a negative percent?
And I had a good question on this. Is that a negative percent? No, this is growing. This population's growing. If I come back up here, the B is the growth rate. Notice how there's a negative in front of the B. So you can ignore the negative on that. So the B term is your negative, right? Because this thing, if you look at it here, right, like over time, it's approaching a certain population. It's got a horizontal asymptote, right? As t goes to infinity, it's approaching a population, but it has kind of a limiting factor, if you will. But there is a growth rate here, 2.515%. So, yeah, I should have actually, when I did this, I should have just ignored the negative. Sorry about that. Don't mean to throw you off on that. All right, let's go ahead and use the function to approximate the Canadian population on January 1st, 2015. Well, 2015 is how many years since 1900? Yeah. So we're figuring it out for 115 years is exactly right. So now I've just got to punch it in. P of 115 is 55.1 over 1 plus 9.6 e negative 0.02515 times 115. And this will end up being if you go negative 0.02515 times 115, you'll get e to the negative 2.89225, and then go e to that. E to that ends up being 0.05545. Then do that times 9.6. You get 0.053233. So 55.1 divided by 1.053233 is approximately 36. And remember, this is in millions. So in the year January 1st, 2015, you have about 36 million in the Canadian population. All right, this last one says, well, from this model, when will the Canadian population reach 45 million? So 45 would go right there. And we're going to have to solve for t. Now I'm going to get that on top, so I'm going to multiply both sides by that denominator. So I have 45 times that 1 plus 9.6 e to the negative 0.02515 t equals 55. I'm going to go ahead and distribute that. Actually, you know what? Instead of distributing, I'm just going to divide it out. So I have 1 plus 9.6 e to the negative 0.02515 t equals 55 over 45, or I'm sorry, 55.1, sorry, over 45 gives you 1.2244. Keeps going. Subtract 1. .2244 blah blah blah. Divide by 9.6. And you get 0.0233796. Now I run the natural log on both sides. I'll undo e. And then I divide by 8.02515. And t ends up being 149. So that's saying the population, it takes 149 years. So it takes 149 years from 1900 to reach 45 million population in Canada, right? In other words, the year 2049 is the year that they will reach 45 million from our logistic growth model, right? Well, that's it. Thanks so much for watching. See you next time.